The wind cut different across the Dakota plains in late 1888. Hans Muller learned that his first winter, when his surface hearth cabin dropped to 5 degrees above freezing, despite burning 3 cords of wood in 12 hours, ice forming on the inside walls while 40-mile-per-hour gusts ripped heat from his standard stone fireplace. He had built his shelter exactly the way every homesteader manual said to build it. Surface-level hearth, stone chimney, tight log walls, proven and trusted. Across the territory, settlers were losing the same battle in cabins built by the book and failing by the season. Neighbors called his underground digging prairie fancy, when Hans quietly applied a fire tunnel method, learned from a Lakota elder. While standard hearths kept failing in the wind, his underground system heated his cabin 52 degrees warmer using half the wood. Today, we'll break down the exact steps and principles behind this forgotten technique. What did Hans understand about draft and heat flow that every other frontier builder missed? The Dakota Territory stretched endlessly in all directions from Hans Muller's claim, a landscape where timber grew only in narrow strips along distant creek beds, and the nearest neighbor lived 3 miles across open grassland. Winter arrived in October and stayed through April, bringing sustained winds that rarely dropped below 20 miles per hour and frequent storms that doubled that force. Fuel meant a 2-day wagon journey to the timber breaks, then another day splitting and hauling loads that cost more than most settlers earned in a month of farm work. Every cord of wood represented backbreaking labor and precious cash that homesteaders could barely spare. The accepted wisdom came directly from the U.S. Army Corps of Engineers Field Manual and every emigrant guidebook printed in Chicago or St. Louis. Build your hearth at floor level in the center of the main room. Construct a stone firebox with clay mortar. Run a straight chimney up through the roof peak, and maintain a steady burn with seasoned hardwood. The method had worked for generations of farmers in Ohio and Pennsylvania, and military engineers had tested it in frontier posts across the West. Settlement agents recommended it because surface hearths were simple to build, required no special tools, and used familiar materials that any carpenter could handle. Hans followed these instructions precisely when he raised his cabin in September of 1888. He laid a fieldstone foundation for the firebox, built the walls 18 inches thick with local limestone, and crafted a clay-lined chimney that drew smoke cleanly on calm days. His neighbors John Thompson and the Campbell family had built identical hearths the previous season, and the territorial surveyor had approved the design when he inspected new homesteads that summer. The system looked solid, professional, and exactly like the diagrams in the official guides. The failure came in waves throughout that first winter, each storm revealing new problems that the manuals had never mentioned. When winds exceeded 30 miles per hour, the chimney created a reverse draft that filled the cabin with smoke and scattered burning embers across the floor. The straight vertical chimney acted like a wind tunnel, pulling heated air up and out of the room faster than the fire could warm it. Snow driven horizontally by prairie gusts melted against the hot chimney stones, then froze into ice dams that cracked the mortar and sent water streaming down the interior walls. Most critically, the open firebox sat directly in the path of wind currents that leaked through every gap in the log walls, creating a convection effect that swept heat away from the living space and up the chimney before it could warm the room. Thompson burned through 8 cords of wood by February and still woke to find frost covering his bedding on stormy nights. The Campbell family's hearth cracked completely during a January blizzard, forcing them to crowd into their neighbor's already overcrowded cabin until spring repairs could begin. Across the territory, homesteaders faced the same pattern: excessive fuel consumption, inadequate heating, structural damage from freeze-thaw cycles, and repair costs that consumed their limited cash reserves. Hans brought a different background to these problems than most prairie settlers. His father Friedrich had operated a blacksmith forge in Bavaria, where winters were harsh and fuel expensive, forcing craftsmen to develop efficient heating methods that extracted maximum warmth from every log. Hans had apprenticed in that forge, learning to control airflow, manage draft systems, and build fire chambers that retained heat instead of losing it to wind and poor design. When he immigrated to America in 1885, he worked 3 years as a carpenter in Minnesota, gaining experience with frontier construction techniques and cold climate building methods that most homesteaders lacked. More importantly, Hans had spent time with Wikasa Tanka, a Lakota elder who hunted in the region during seasonal migrations. The old man had shown him fire pits used by hunting parties on the open plains, twin-hole systems that burned efficiently in 40-mile-per-hour winds and left no visible smoke to alert game animals or hostile parties. These pits worked on principles that seemed to contradict everything the Army manuals taught about proper hearth construction, using underground chambers and horizontal airflow instead of vertical chimneys and surface-level fires. When Hans began digging test holes in his cabin floor during March of 1889, his neighbors reacted with skepticism that quickly turned to mockery. Thompson called it Indian trickery and insisted that any man who followed proper construction methods and burned enough wood could stay warm through any winter. The local supply merchant, who profited from selling massive quantities of expensive firewood, dismissed the underground approach as over-engineered nonsense that wastes good digging time. Even Hans's wife questioned the wisdom of tearing up their cabin floor when spring was coming, and the standard hearth, however inefficient, had at least kept them alive through the worst months. The social pressure reflected deeper cultural tensions between established frontier wisdom and traditional knowledge from indigenous sources. Most homesteaders viewed their struggles with heating as natural consequences of harsh climate that required endurance rather than innovation. The idea that a different approach might solve the problem challenged their assumptions about proper American building methods and suggested that their expensive, labor-intensive standard techniques were fundamentally flawed. Hans's early experiments were crude and partially successful at best. He dug a shallow pit beneath his existing hearth and tried to direct airflow horizontally instead of vertically, but without proper understanding of tunnel dimensions or air supply management. The system worked better than the surface fire during moderate winds, but still consumed too much fuel and produced uneven heating. His neighbors watched these partial failures as confirmation that conventional methods, despite their problems, remained the only reliable choice for prairie survival. The central conflict had crystallized into a clear choice between two fundamentally different approaches to frontier heating. The conventional surface hearth method relied on brute force: burn more wood, build thicker walls, endure the inefficiencies, and accept high fuel costs as unavoidable consequences of prairie life. The alternative approach, combining indigenous fire techniques with immigrant craft knowledge, required understanding airflow principles, underground construction, and integrated system design that most settlers had never encountered. Hans stood alone between these two philosophies, testing ideas that could revolutionize frontier heating or prove to be expensive failures that wasted precious resources his family could not afford to lose. Spring arrived early in 1889, giving Hans the opportunity to completely reconstruct his heating system before the next winter tested his theories against Dakota reality. The design that emerged combined two distinct technical traditions in ways that neither source had originally intended, creating a hybrid system that addressed the specific challenges of prairie wind patterns and extreme temperature differentials. Wikasa Tanka's hunting fire technique required precise excavation dimensions that had been refined through generations of winter survival on the open plains. The fire pit measured exactly 12 inches in diameter and 18 inches deep, carved into the earth floor of the cabin with walls sloped inward to concentrate heat and prevent collapse. The intake, or hole positioned 12 inches away from the fire chamber, was smaller at 6 inches across and 10 inches deep, designed to capture outside air without creating excessive draft that would waste fuel. The critical component was the connecting tunnel, dug 4 inches in diameter and angled slightly upward from the intake toward the fire chamber to ensure proper airflow direction. The tunnel construction demanded skills that most homesteaders lacked. Hans used his carpenter's tools to create smooth, even walls that would not restrict airflow or create turbulence that might disrupt the combustion process. He lined the tunnel with flat stones fitted precisely together, eliminating gaps that could leak air or allow the passage to fill with debris. The fire chamber itself received a more sophisticated treatment, with mortared fieldstone walls that would retain heat and reflect it upward into the living space rather than absorbing it into the surrounding earth. Friedrich Miller's forge experience provided the theoretical framework that made the Lakota technique work efficiently in a permanent structure. The downdraft principle relied on creating a controlled combustion environment where fresh oxygen entered at the base of the fire while exhaust gases rose naturally through convection. This required understanding the relationship between air supply, fuel consumption rate, and heat output that blacksmiths used to maintain consistent temperatures for metalworking. Hans applied this knowledge by calculating the proper ratio between tunnel diameter, fire chamber volume, and the cabin's interior space to achieve optimal heat distribution. The physics of the system reversed the problems that plagued surface hearths during windstorms. Instead of wind disrupting the fire and stealing heat, the underground chamber created a sealed combustion environment where external air pressure actually improved performance. Strong winds increased the pressure differential between the intake hole and the fire chamber exhaust, forcing more oxygen through the tunnel and intensifying the burn without wasting heat. The earth surrounding the fire pit acted as thermal mass, absorbing excess heat during active burning and radiating it steadily for hours after the fire died down. Construction began in April, when the ground thawed enough for digging, but before spring, planting demanded Hans's full attention. He removed the floorboards above his failed surface hearth and began excavating the precise dimensions that Wikasatanka had demonstrated the previous fall. The work proceeded slowly because every measurement had to be exact. A tunnel too large would waste fuel through excessive airflow, while one too small would starve the fire and create incomplete combustion that filled the cabin with smoke. The intake hole presented unexpected challenges because it needed to connect with outside air without compromising the cabin's structural integrity. Hans solved this by extending the intake passage horizontally under the cabin wall and creating a discrete opening on the exterior that could be covered during severe storms but remained functional in normal winter conditions. He fitted this opening with a simple wooden damper that allowed him to regulate airflow based on wind conditions and desired heat output. Testing began in May with small fires that revealed design flaws requiring immediate correction. The initial tunnel angle proved too steep, causing poor airflow and uneven burning that wasted fuel. Hans re-excavated the passage with a gentler slope of approximately 15 degrees, which improved oxygen delivery and created the steady draw that maintained consistent combustion. He also discovered that the fire chamber needed a sand and clay bottom layer to prevent heat loss into the earth and provide a stable base for burning hardwood logs. The first controlled comparison occurred during an unseasonably cold snap in late May when outside temperatures dropped to 32 degrees Fahrenheit with 25-mile-per-hour winds, conditions similar to mild winter weather but perfect for testing without risking his family's survival. Hans burned 1 cord of split oak in his underground system over a 10-hour period, while John Thompson simultaneously burned 2 cords in his rebuilt surface hearth during the same interval. Hans's cabin maintained an interior temperature of 68 degrees, while Thompson struggled to reach 55 degrees despite using twice the fuel. The tunnel fire's efficiency became apparent through multiple measurable factors beyond simple temperature differences. Combustion was more complete, producing less smoke and leaving minimal ash residue compared to surface fires that wasted energy through incomplete burning. The steady airflow eliminated the irregular heat output that characterized conventional hearths, where blazing periods alternated with smoldering phases that provided little useful warmth. Most importantly, the underground system continued radiating heat for 3 to 4 hours after the fire died completely, as the surrounding earth and stone liner slowly released their stored thermal energy. Hans documented these early results carefully, measuring fuel consumption, burning duration, interior temperatures, and heat retention periods with the precision he had learned in his father's forge. A typical test burn used 18 pounds of split oak, burned for 6 hours at a steady rate, and maintained the cabin at comfortable temperatures for an additional 4 hours using only residual heat from the thermal mass. The same amount of wood in Thompson's surface hearth provided effective heating for only 3 hours and required constant attention to maintain even burning. The system's performance during wind conditions proved even more dramatic. While surface fires struggled against air currents that disrupted combustion and stole heat, the underground chamber actually improved during storms as increased air pressure drove more oxygen through the tunnel and intensified the burn. Hans measured interior temperatures during a spring thunderstorm with 40-mile-per-hour gusts, and found that his heating system performed better under these conditions than during calm weather, reaching 72 degrees inside while the storm raged. By late summer, Hans had refined the design into a reliable system that addressed every major weakness of conventional prairie heating methods. The underground fire tunnel eliminated wind disruption, reduced fuel consumption by approximately 60%, provided steady heat output without constant attention, and continued warming the cabin long after active burning ceased. The technical success was undeniable, but the coming winter would provide the ultimate test of whether this hybrid system could keep his family alive and comfortable through the extended cold season that had defeated so many conventional approaches. The efficient fire tunnel solved the problem of heat generation, but Hans quickly discovered that producing heat and retaining it were entirely separate challenges requiring different technical solutions. Even his refined underground system lost much of its advantage when heat escaped through the cabin's permeable envelope, flowing out through gaps between logs, rising through the inadequately sealed roof, and radiating down into the cold earth through the wooden floor. The problem became apparent during his first autumn tests when outside temperatures dropped to 40 degrees, but the cabin interior struggled to maintain 60 degrees despite the tunnel fire burning at optimal efficiency. The root issue lay in the fundamental construction methods that frontier builders used for speed and simplicity rather than thermal performance. Standard log cabin walls relied on chinking, stuffing moss, clay, or wood chips between the horizontal logs, but this approach created thousands of small air leaks that collectively allowed massive heat loss. The gaps expanded and contracted with temperature changes, creating pathways for cold air infiltration that no amount of additional burning could overcome. Even worse, the wooden floor sat directly on the ground with minimal insulation, creating a thermal bridge that conducted heat downward into the earth where it provided no benefit to the occupants. Hans recognized these problems from his father's teachings about Bavarian building techniques, where long winters and expensive fuel had forced craftsmen to develop sophisticated approaches to heat retention. Friedrich had explained how German masons used thermal mass, materials that absorbed, stored, and slowly released heat to smooth out temperature fluctuations and maximize the value of every piece of fuel burned. The principle worked by creating a thermal flywheel effect where excess heat from active burning was captured in dense materials and then radiated back into the living space over extended periods. The first component Hans implemented was a comprehensive floor system that transformed the cabin's thermal behavior. He excavated the entire floor area to a depth of 18 inches below the original surface, then built up layers of specific materials designed to work with the underground fire tunnel. The bottom layer consisted of 6 inches of dry sand that provided drainage and prevented moisture from wicking up from the ground. Above this, he placed 8 inches of clay mixed with chopped prairie grass and sand, creating a dense thermal mass that would absorb and store heat from the fire chamber. The top layer represented the most innovative element of the system, a 2-inch coating of clay, sand, and finely chopped straw that created a smooth, sealed surface that eliminated air infiltration through the floor while providing additional thermal storage capacity. This mixture hardened into a surface similar to adobe construction, with the organic material creating tiny air pockets that improved insulation while the clay provided thermal mass. The entire floor system weighed approximately 8 tons when completed, creating enormous heat storage capacity that could absorb energy during active burning and release it gradually over 6 to 8 hours. Construction of the floor system required techniques that Hans adapted from both German and frontier practices. He sourced clay from a deposit 2 miles north of his claim, selecting material with the proper plasticity that would hold together without cracking as it dried. The straw came from his own wheat harvest, chopped into pieces roughly 1 inch long, to provide reinforcement without creating weak points in the dried surface. Mixing was accomplished by adding water gradually while trampling the materials with his boots, a laborious process that took 3 full days to complete properly. The wall treatment addressed air infiltration through an approach that combined old-world plastering techniques with available prairie materials. Hans applied a base coat of clay mixed with sand and chopped grass over the interior surfaces of all log walls, filling gaps and creating a continuous thermal barrier. This initial layer, approximately 1 inch thick, sealed the major air leaks while providing modest thermal mass. Over this base, he applied a finish coat of finer clay mixed with sand that created a smooth surface and eliminated the remaining pathways for air movement. The most ambitious component was the installation of sod blocks along the interior walls up to a height of 4 feet from the floor. Hans cut these blocks from virgin prairie sod, selecting pieces with deep root systems that would maintain structural integrity when stacked. Each block measured roughly 12 inches wide, 18 inches long, and 6 inches thick, creating substantial thermal mass while providing additional insulation against heat loss through the log walls. The sod blocks were stacked like masonry with the grass side facing inward, creating an attractive and functional interior finish that dramatically improved the cabin's thermal performance. Erik Larsen, a Norwegian immigrant who had arrived in Dakota Territory 5 years earlier, provided crucial knowledge about integrating fuel storage with thermal mass systems. Larsen had built a fuel storage lean-to against the north wall of his cabin, creating a buffer zone that reduced heat loss while keeping firewood dry and accessible. Hans adapted this concept by constructing a similar lean-to that extended the cabin's thermal envelope and provided convenient wood storage that eliminated the need to venture outside during severe weather. The lean-to construction used earth berming on 3 sides, with only the interior wall connecting to the main cabin left unprotected. Hans piled excavated earth from his floor construction against the exterior walls of the lean-to to a height of 3 feet, creating additional thermal mass and wind protection. The berm design reduced temperature swings in the wood storage area and prevented the freeze-thaw cycles that could crack stored logs and reduce their burning efficiency. Integration of these envelope improvements with the existing fire tunnel created synergistic effects that neither system could achieve independently. The thermal mass absorbed excess heat during peak burning periods and released it steadily during the long hours between fuel loadings, smoothing out temperature fluctuations and maintaining comfortable conditions with less frequent attention to the fire. The sealed envelope prevented the heated air from escaping, ensuring that energy stored in the thermal mass remained available to warm the living space rather than dissipating into the outside environment. Testing of the complete system began in November when the first serious cold snap dropped outside temperatures to 15 degrees Fahrenheit with steady 20-mile-per-hour winds. Hans burned 1.5 cords of oak over a 72-hour period while maintaining interior temperatures between 65 and 72 degrees. The thermal mass system demonstrated its value during the overnight periods when he allowed the fire to burn down to coals. Interior temperatures dropped only 6 degrees over 8 hours compared to the 20-degree drops he had measured the previous winter with conventional heating. The envelope improvements also revealed unexpected benefits beyond simple heat retention. The sealed interior eliminated drafts that had previously made the cabin uncomfortable even when temperatures were adequate, creating a more livable environment that felt warmer than the thermometer indicated. Humidity levels stabilized because the thermal mass absorbed and released moisture along with heat, preventing the excessive dryness that plagued most frontier cabins during winter heating season. Most importantly, the integrated system reduced fuel consumption by an additional 30% compared to the fire tunnel alone, proving that heat retention was as important as efficient heat generation for prairie survival. The underground fire tunnel and thermal envelope created an efficient heating system, but Hans discovered that even the most sophisticated combustion chamber could not overcome the fundamental problem of poor fuel quality that plagued most frontier homesteaders. The issue became apparent during his December testing when a delivery of supposedly seasoned hardwood performed dramatically worse than expected, requiring constant attention and producing uneven heat that undermined all the technical advantages he had built into his heating system. Most settlers acquired firewood through whatever means proved most expedient, buying semi-green logs from traveling suppliers, cutting standing dead timber when they could find it, or trading labor for wood that neighbors had cut months earlier without proper drying techniques. The moisture content of this fuel varied wildly, from relatively dry pieces at 15% moisture to freshly cut logs containing 40% water by weight. High moisture wood created multiple problems that compounded each other. Incomplete combustion that wasted energy boiling off water instead of producing heat, excessive smoke that indicated poor burn efficiency, and irregular flame temperatures that prevented the tunnel system from reaching its optimal performance range. The physics of wood combustion demanded specific moisture thresholds that most homesteaders neither understood nor measured. When moisture content exceeded 20%, a significant portion of the fire's energy was consumed simply evaporating water from the wood fibers before combustion could begin. This process cooled the fire chamber, reduced flame temperature, and created incomplete burning that filled the cabin with smoke while producing minimal useful heat. Even worse, wet wood burned unevenly, with some sections blazing while others smoldered, creating temperature fluctuations that prevented the thermal mass system from storing and releasing heat in the steady patterns that made the underground system so efficient. Hans addressed this challenge by developing a comprehensive fuel preparation and storage system that treated wood processing as an integral component of his heating technology rather than a separate chore. His approach combined techniques learned from multiple sources, beginning with splitting methods that his father had used in the Bavarian forge to prepare specific types of fuel for metalworking applications. Instead of splitting logs into the typical 4 to 6 pieces that most settlers used, Hans split each log into thin slabs approximately 1 inch thick and 6 to 8 inches wide, maximizing surface area exposure to air movement and dramatically accelerating the drying process. The splitting technique required modifications to standard frontier practice because thin slabs demanded different approaches than conventional cordwood preparation. Hans used a sharp splitting axe rather than a maul, working with the wood grain to create smooth surfaces that would dry evenly without checking or warping. He split each log while it was still green, within days of cutting, because dried wood often shattered into unusable fragments when split into such thin sections. The process was more labor-intensive than conventional splitting, but produced fuel that dried in weeks rather than months, and burned with consistent, predictable performance. Storage methods proved equally critical to maintaining fuel quality throughout the long prairie winter. Hans constructed elevated platforms using scrap lumber and stones, creating a foundation that kept stacked wood 6 inches above ground level and allowed air circulation underneath the entire fuel pile. The platform design eliminated ground moisture that could re-wet dried wood and prevented contact with snow that accumulated around the cabin during winter storms. Each platform measured 8 feet by 12 feet, providing sufficient space for approximately 2 cords of split slabs, while maintaining the proper spacing for air circulation. The stacking pattern followed principles that Robert Blackhorse, a Cree carpenter who worked seasonally in the territory, had demonstrated during a visit to Hans's homestead in October. Blackhorse's technique created alternating layers with pieces running perpendicular to each other, similar to log cabin construction but with crucial spacing modifications that promoted airflow through the entire stack. Each layer included gaps of 2 to 3 inches between individual pieces, creating channels for air movement that carried moisture away from the wood surfaces and prevented the fungal growth that could ruin stored fuel. Weather protection represented the most innovative aspect of the storage system, based on Blackhorse's explanation of traditional methods used by Cree hunting parties during extended winter expeditions. Instead of completely covering the wood pile, which trapped moisture and prevented proper drying, Hans built a roof structure that protected only the top surface while leaving the sides completely open to wind and air movement. The roof consisted of overlapping pine boards pitched at a steep angle to shed rain and snow, supported by posts that elevated it 18 inches above the top layer of wood to maintain air circulation. Moisture measurement became a critical component of the fuel management system, though Hans had to develop practical field methods since precision instruments were unavailable on the frontier. He used a simple weight loss technique, selecting sample pieces from each batch of split wood and weighing them on a small scale he had brought from Minnesota. After drying the samples in his oven for several hours, he reweighed them and calculated moisture content based on the weight difference. Wood with less than 15% moisture burned cleanly and efficiently in his tunnel system, while pieces exceeding 20% produced the smoking, inefficient combustion that wasted fuel and undermined heating performance. The integrated fuel system required advanced planning that most homesteaders avoided because of the labor and storage space demands involved. Hans began preparing wood for the following winter immediately after each heating season ended, splitting and stacking logs during the warm months when outdoor work was pleasant and wood dried rapidly in the prairie sun and wind. By late summer, he typically had 4 to 5 cords of properly dried fuel ready for the approaching cold season, compared to most neighbors who scrambled to acquire adequate supplies after winter had already begun. Performance testing during the winter of 1889 to 1890 revealed the dramatic impact of fuel quality on overall system efficiency. During a 10-day cold period with outside temperatures averaging minus 20 degrees Fahrenheit, Hans burned 2½ cords of his thin split properly dried oak and maintained interior temperatures averaging 70 degrees with minimal attention required. John Thompson, burning 4 cords of conventional semi-green firewood in his rebuilt surface hearth, struggled to maintain 55 degrees and required stoking every hour during the coldest nights. The fuel preparation system also eliminated the irregular performance that had plagued Hans's early tunnel experiments. Properly dried thin slabs ignited quickly, burned at consistent temperatures, and produced the steady heat output that allowed his thermal mass system to function optimally. Each loading of the fire chamber provided predictable heating duration, typically maintaining comfortable temperatures for 4 to 5 hours compared to the 1 to 2 hours he had achieved with variable quality wood. This consistency allowed him to establish a regular firing schedule that maintained warmth throughout the night, with only one midnight loading, a dramatic improvement over the constant attention that conventional systems required. Perhaps most importantly, the integrated fuel system proved its value during supply emergencies when normal wood sources became unavailable. In February, a severe blizzard blocked transportation routes for 2 weeks, preventing the usual wood deliveries that most homesteaders depended upon. Hans's advanced preparation and efficient storage system provided adequate fuel reserves to maintain normal heating throughout the crisis, while several neighbors faced dangerous situations when their inadequate supplies ran low during the extended cold period that followed the storm. The winter of 1892 brought the ultimate test of Hans's integrated heating system in the form of a sustained Arctic outbreak that territorial weather observers would later record as the most severe on the northern plains in over a decade. The crisis began in late January with a massive storm system that generated sustained winds of 45 to 55 miles per hour, while dropping outside temperatures to minus 35 degrees Fahrenheit, conditions that persisted for 7 consecutive days without moderation. The combination of extreme cold and relentless wind created effective temperatures approaching minus 60 degrees, well beyond the survival threshold for conventional frontier heating methods. The storm's severity demanded emergency protocols that Hans had developed specifically for his integrated system, techniques that treated extreme weather as a predictable engineering challenge rather than an unavoidable natural disaster. His approach began with systematic fuel staging 48 hours before the storm arrived, based on weather signs that Wikasatanka had taught him to recognize. Specific cloud formations, wind direction changes, and atmospheric pressure drops that typically preceded major Arctic outbreaks. Hans prepositioned 6 cords of his finest dried oak slabs in the covered lean-to immediately adjacent to his cabin, eliminating the need to venture outside for fuel during the worst conditions. The emergency firing protocol involved modifying his normal heating schedule to maintain continuous combustion rather than allowing the fire to cycle through burning and smoldering phases. This required loading the tunnel fire chamber every 2 hours with precisely calculated amounts of fuel, typically 12 to 15 thin oak slabs, that would burn completely before the next loading without creating excessive heat that might crack his thermal mass system. The technique demanded careful attention to flame color and tunnel draft sounds that indicated optimal combustion, skills that Hans had developed through 2 years of systematic observation and adjustment. Interior climate control during extreme conditions revealed previously unknown capabilities of the integrated thermal management system. Hans discovered that he could create distinct temperature zones within his cabin by controlling the rate of heat release from different sections of his thermal mass floor. By concentrating the fire chamber's heat output in specific areas during peak burning periods, he could warm the floor thermal mass unevenly, then redistribute that stored energy by opening or closing interior doors and adjusting airflow patterns. This zoning technique allowed him to maintain 72 degrees in the main living area while keeping the sleeping area at a more moderate 65 degrees, conserving fuel while ensuring comfort in the spaces where his family spent the most time. The storm also tested the structural resilience of components that had never faced such sustained stress. Wind pressure against the cabin created negative air pressure that dramatically increased the tunnel system's efficiency, drawing outside air through the intake hole with much greater force than normal. Conditions generated. Hans monitored this effect by listening to the characteristic whistle that indicated optimal airflow and adjusting his fuel loading schedule to take advantage of the enhanced combustion without overheating the fire chamber. The enhanced draft allowed him to burn smaller fuel loads more completely, actually reducing his fuel consumption compared to milder weather despite the increased heating demands. Emergency water management became a critical component of extreme weather survival that Hans had not fully anticipated in his original system design. The severe cold froze his normal water sources and made trips to the well impossible during the worst periods. He solved this problem by placing large iron pots directly over the fire chamber opening, using waste heat from the tunnel system to melt snow and ice collected before the storm intensified. This technique provided adequate water for cooking and drinking without requiring additional fuel, demonstrating how the integrated system could support multiple survival needs simultaneously. John Thompson's experience during the same storm provided a stark comparison that validated every aspect of Hans's technical innovations. Thompson's rebuilt surface hearth, despite improvements made after previous failures, consumed 8 cords of wood during the 7-day emergency while struggling to maintain interior temperatures above 40 degrees. His cabin suffered multiple structural failures: ice dams that cracked the chimney foundation, frost heaving that opened gaps in the log walls, and floor damage from repeated freeze-thaw cycles that occurred when his heating system could not maintain consistent temperatures. Most seriously, Thompson's livestock shelter failed completely, resulting in the loss of 4 hogs and 6 chickens that represented significant economic value. The Campbell family faced even more severe consequences when their conventional heating system proved inadequate for the sustained extreme conditions. By the 4th day of the storm, they had exhausted their fuel reserves and were forced to burn furniture and interior wood fixtures to maintain minimal heat. Mary Campbell later reported that interior temperatures in their cabin dropped to 20 degrees on the worst night, creating dangerous conditions that threatened the health of their youngest children. Only the intervention of neighbors who shared emergency fuel supplies prevented a potential tragedy. Hans's systematic documentation during the crisis provided precise measurements that demonstrated the quantitative superiority of his integrated approach. He recorded fuel consumption of 2 1/4 cords over the 7-day period while maintaining interior temperatures that never dropped below 68 degrees. His family remained comfortable and healthy throughout the emergency, with adequate food preparation capability and reliable water supplies. The economic implications were equally dramatic. While his neighbors faced repair costs averaging $200 to $300 each, Hans's cabin suffered no structural damage and required no post-storm repairs. The performance differential during this extreme test finally convinced local skeptics that Hans's methods represented genuine technical advancement rather than eccentric experimentation. Samuel Reed, the territorial surveyor who had previously dismissed underground heating as impractical, visited Hans's homestead immediately after the storm to measure and document the system's components. Reed's official report, filed with the territorial government in March of 1892, included detailed drawings of the fire tunnel construction and specific recommendations for incorporating similar techniques into official frontier building guidelines. Mary Campbell became the first neighbor to implement Hans's integrated heating approach, beginning construction of her own tunnel system in the spring of 1892 with direct technical assistance from Hans and materials shared from his supply stockpiles. Her successful replication of the system during the following winter provided independent validation that the techniques could be transferred to other builders and adapted to different cabin configurations without losing their essential effectiveness. The transformation of community attitudes reflected a broader shift from dismissing traditional knowledge to actively seeking methods that address the specific challenges of prairie survival. By 1893, 3 additional families in the township had begun implementing variations of Hans's system, creating a network of knowledge sharing that ensured the techniques would survive and evolve beyond their original application. The underground fire tunnel had evolved from a mocked innovation into an accepted component of serious frontier construction, proving that practical results ultimately overcome cultural resistance when survival depends on technical competence.